our speakers cannot come.
Recording in progress.
And so, yeah, take your time. We have this spare 15 minutes actually for two speakers. So if you have more materials, please, yeah.
Okay, yeah. Actually, Turkish is completely the midnight, so I will keep the time.
Okay.
So, can you see my screen?
Yeah, I can see your screen.
Okay. This moment. Okay. So, can you hear my voice clear?
Yeah, it's pretty clear.
Okay. So, can I start right now?
Okay, so let's then start our this afternoon session of seminar 1. I say afternoon, but of course it's 11 a.m. in Texas, and it just shows that this is really an international event all over the globe. I'm thankful to Olga for honor to preside at this session. And our first speaker is Liming Chen from Shanghai Jiao Tong University, who will speak on laser-driven ultra-high charge electron acceleration for nuclear applications. So Liming, please go on with your talk.
Okay, thank you. So at first, I'd like to thank the chair giving me the chance to present our progress in recent years concerning the laser-driven high-charge electron acceleration for nuclear applications. I'm Liming Chen from Shanghai Jiao Tong University. Excuse me? Well, why? Okay. So this is my presentation online. So at first, I'd like to briefly introduce the motivation, and then followed by the high charge electron accelerations and enhanced Bellatron, X-ray, or gamma ray sources, and then applications in the nuclear physics. So the electron charge, of course, is very important for some applications. For example, for the ultra-fast radiation, such as the Bellatron radiation. The Bellatron radiation is a kind of combination of the laser plasma accelerator and the plasma awakener. So we can call it kind of tabletop synchrotron radiations. So this kind of radiation, the photon yield, energy, and its brightness is really controlled by the electron bunch, the electron energy, the electron charge, and its oscillation amplitude. So the electron charge is really very important for the flux of the Bellatron radiation. And also the Thomson scattering, the photon yield of the Thomson scattering is really linearly proportional with the electron charge with this formula. So the electron charge is very important, but unfortunately, during the next wave field acceleration means the electron will be stably injected into the wave field and accelerated stably. Stable means the charge, the electron charge is really limited by the matched bubble electron acceleration situations. So the electron energy is decided by this formula, and its charge is decided by this one. It's a matched condition. So experimentally, our experiment shows an electron charge is really limited below than, for example, several hundred picocoulomb. So that's much lower than the beam loading effects. So how to increase the accelerated electron beam charge is really an important topic. So we need to find some another way away from the matched condition for the bubble situation. Okay, so we need to find some way to do it. Okay, the first method we found in our research work. For example, we use this kind of oscillation injection method. This oscillation injection means we choose the plasma density slightly higher than the matched condition. So in this case, we can observe experimentally and also simulation to show the charge of the second electron beam. We can obtain in experiment is 600 picocoulomb. It's 1.5 times higher than the matched condition. So that means we use this kind of oscillation injection method. These injections occurred during the two weak field combined to a big one. So in this case, the real part of this, the first weak field, the electrons were injected into the weak field and form a big bubble. So in this case, the second bunch of electrons will have higher energy, high charge, and big oscillation amplitude. It's very good for the high charge electron acceleration and also enhanced electron radiations. So this is the first method. And the second one, we choose a petawatt, a picosecond laser shining on a solid target with some free plasma. So in this case, we shining on the solid target with large incident angle, for example, 78 degrees. So in this case, we can observe just along from the target reflection directions, there is a very collimated electron beam with huge charge. The charge can reach to 100 nanocoulomb. So it's very useful for some applications. We performed this experiment several years ago at Titan laser at Northern Stephen Morrison Laboratory. But the solid target, that means the electron energy actually is not so high. It's only 10 MeV level. So in these 2 years, actually, we found the third method is a more effective way. We tightly focused the 100 terawatt laser to the high density, again, the high density plasma. So we really got the matched condition, this matched profile conditions. So in this case, because the matched condition correspond to the beam loading charge for the electrons is approximately 2 nanocoulomb. So in this case, okay, our experiment shows, okay, a quite collimated electron beam with the charge is approximately 20 nanocoulomb, and also the electron energy can reach to 40 MeV. So this is a quite collimated, good collimated, and high charge and very high conversion efficiency. I mean, the laser convert to the electron energy can reach to 12%. So it's a really high level. Our simulation shows the continuously ionized electrons were continuously injected into several laser weak field. So in this case, and for each weak field, the electron charge reaches to the beam loading. So that means approximately 10 weak field reaches to the beam loading. So in this case, we can got approximately, according to our simulations, approximately 20 nanocoulomb. So in this case, we explained the experimental results we achieved. Okay. So with this method, we really got a highly collimated and ultra high charge electron beam. Okay, so that means with high laser intensity and also high plasma density is the right way to get the high charge electrons and enhanced Beachtron X-rays. So we actually this year we use the CAEP petawatt laser and also high density plasmas. We perform another experiment, and we really got this good collimated with only 5 degree and charge 200 nanocoulomb. So the Beachtron X-ray yield can reach to 10 to 13 photons per shot. So it's quite high. And the conversion efficiency can reach to 10 to minus 4. And the laser electron conversion efficiency 2.6. So it seems this conversion efficiency actually compared to the 100 terawatt case is not so high, but still high enough compared to some other method. In our case, we believe the DLA mechanism is really stimulated, and actually the plasma shows a kind of channel situations, and this channel have huge electromagnetic self-generated magnetic field. So this is evident of the DLA, the direct laser acceleration. Okay, so it's quite high level. Of course, if we choose more higher density plasma, for example, the near created density plasma, well, it seems the conversion efficiency is not so high, and the electron charge becomes lower. That means maybe we need to continuously increase laser intensities. And this target density actually is too high. Okay. So we use this kind of high charge electron accelerated electron beam for the nuclear excitations. Okay. So actually, the nuclear excitation method, we have the beam-driven nuclear excitation and the Coulomb excitation, and the excitation via the gamma nuclear reactions, or the nuclear excitation through the electron capture, or the the leak or lit. So all these method, because of the cross section is somewhat very low. For example, for the Coulomb excitation, usually the cross section is smaller than microbarn. So we really need the high beam density to stimulate this kind of excitation. But unfortunately, right now some facilities, for example, some accelerators or some colliders, the peak density of the beam or the radiation, the density actually at a level of 10 to 16. For example, the electron accelerator, BEPC, the Beijing Electron Positron Collider or something, the density is only 10 to 16. and some ion accelerators is even lower. So this kind of low beam density or current is hard to excite and accumulate enough nuclear in exciting state. So, limited by the peak current of the driven beam, the nuclear excitation or reaction rate of current accelerators or colliders is hard to estimate large number of nuclear isomers with very small cross-section and short lifetime, for example, with lifetime shorter than nanosecond. So it's very difficult. Fortunately, we have the laser weak field accelerator. So let's compare the Beijing collider. It's at a density 5 times 10 to 16. And the laser weak field accelerator, we really have the density 2 times 10 to 21. So the density is actually 4 or 5 times higher than the traditional accelerators. Here is BEPC, BEPC2, LC, LS, and FACET. And for the this weak field accelerators for DLA, LWFA, or something, right now we got this venue. It's 4 orders higher than the traditional accelerators. So in this case, we think we can construct a kind of laser plasma collider or laser plasma exciter for nuclear applications. For example, if we use a laser weak field accelerated electron beam and hit on some converter target and produce neutron. So in this case, actually in our experiment several years ago, and we really got the neutron yield per joule correspond to the high, almost the highest level, but with much lower electron energy. So of course, we can also produce some positrons singles. The interesting thing is last year we have a publication to show we use this kind of highly charged electron beam hit on a converter and produce through the gamma N reaction, we produce this kind of neutron sources with a diameter 200 nanometer micro. So according to our calculations, we can show the fluence rate of this neutron source can reach to 10 to 20 neutrons per square centimeter per second. So it's wow. Actually, it's 3 orders higher than the simulation source. For example, the Dongguan simulation source, and it's wow close to the supernova, 10 to 22. So this kind of source is part of is potential to be used for to study the S process or the rapid process of the neutron absorption. And this neutron source with duration approximately 100 picocoulomb. So in this case, it's very suitable for the fast neutron fine absorption spectroscopy applications compared to the simulation sources. So our sources can give this kind of spectroscopy with quite fine structures. And of course, it's also suitable to study the heavy elements and nuclear synthesis reaction because the peak flux is quite high. Okay, and apart from the neutron sources, we also use this kind of method to directly stimulate it to excite the ground state of the krypton 83 clusters from the ground state to the third state, and then the isomers from the third state to the second state, and then it drop to the ground state. So actually we detected the half-life time. It's 1.8 hour, and the exciting efficiency is 3000 per joule. The exciting rate is ground state to the third state and the second state. And we really detected the line is matched for the theoretical calculations. So that means we really directly excited the krypton 83 from the ground state to the second and third state, the isomer. So our simulations to show the nuclear Coulombic excitation from the nonlinear resonant of the cluster. I mean, the electrons will be heated by the laser, and it's traveling along the clusters. So these electrons at first absorb the energy, and it collide with this krypton 83 isomer and excite it. So after our calculation, the peak efficiency of the pumping is the pumping efficiency. The peak efficiency is 10 to 15 particle per second. So it's a very high number. So if we calculate according to the ability of the BEPC2, the Beijing Electron Positron Collider, the peak efficiency is 10 to 10. So it actually is 5 orders higher than the BEPC2, the collider. And all the accelerators is even much lower than 10 to 10. It's only 10 to 6 neighbors. Okay, so our calculations shows actually this isomer excitation cross-section is only lower than 10 to minus 9 barn. See, it's a very, very small value. But even it's so small, we can directly accumulate, excite it. And very recently, we really detected this cross-section with several data, okay? Okay, the cluster, the electron energy actually is not so high. It's only MeV neighbor or several hundred keV neighbor. So we use this kind of accelerated electron beam, try to excite some isomer. For example, the indium 115 isomer, indium 115. So we shining the laser to the nozzle, and we got this kind of optimized electron beam with quite high charge, for example, 20 nanocoulomb, as we mentioned previously. And then we hit this kind of electron beam to the indium target here. Of course, it's yes, at first to a copper converter, convert it to the gamma rays, and then gamma ray incident in the indium target. So in this case, we really can through this kind of gamma reaction to stimulate the indium-115 to indium-115 isomer, and we stimulate the isomers, and we detected for example, the indium-115 isomer, the half lifetime is completely fight for the calculations of the half lifetime, and the peak excitation rate is 1 × 10⁻15 particle per second. So this kind of optimized 100 kiloamp inertial beam, we organize it to excite the indium nuclear isomers with ultra high peak efficiency of 10⁻15 particle per second via the photon nuclear reaction. So this is very effective. Okay, let's go to a summary. The high charge electron acceleration beyond the matched bubble case can be achieved through the oscillation injections or the multi-weak field injection with higher plasma density. And the DLA-like would be the important mechanism for high charge electron acceleration when we use the petawatt laser or the NCD or even solid target. The high charge electron beams or the X-ray or gamma ray emissions are obtained, which is suitable for nuclear physics. This efficient isomer production method can be widely used for pumping isotopes with exciting state lifetime on the picosecond or even femtosecond scale. Okay, thank you for your attention. Okay.
Thank you, Liming, for very impressive talk and impressive results that you presented. And the talk is open for questions. Well, I see Olga has some question, please.
Yeah, Liming, these are super exciting results indeed. Thank you so much. And did you think about realization of gamma ray laser and producing of population inversion? What can you tell about it?
The gamma ray?
The nuclear transition, yeah.
Okay, actually the gamma ray, for example, if we achieved several tens nanocoulomb with energy several tens MeV, so in this case, the gamma ray photon yield we can achieve, it's approximately 10⁻11 photons per shot. Yeah, so it's actually quite high, and I don't know why I cannot go back. Okay. So yeah, there is a figure to show our calculation. Okay, sorry. Okay, okay. Yeah, here actually it's the wow. Yeah. Okay. Photons. Yes. Yes. Photons, and we got this kind of curve, and the photon energy can reaches to several tens MeV, because this is quite good for the GDR, the giant dipole resonant. I mean, the initial energy we have is suitable for generate gamma rays.
Yes, but it's interesting to see if you can actually induce gain to produce population inversion at some nuclear transition, then it would be just tremendous.
Yeah. Yes, we will consider.
Well, because we have time, because third speaker is not available, I want just to mention that we worked for a long time on the problem of gamma ray laser, and once I discussed it with Norman Ramsey, and he suggested to look for spallation sources and to look for nuclear reactors. And I remember I contacted one group actually in Artemis 16 about possibility to use neutron sources from a nuclear reactor, and they told me, okay, we can do it, but it would be maybe, I don't remember exact number, but something like microsecond before the explosion. And they told me, well, we can work together on this project, but I was kind of, skeptical and did not take this risk. But you see, so it's really great that you have such fantastic possibilities. We should have looked into it. Come back to this problem of gamma ray laser. It would be tremendous. Yeah, thank you.
We also think about the gamma ray lasers because that's our dream, right?
Yes.
But unfortunately, I think the most difficult thing for the gamma ray lasers is try to find a suitable isomer. Try to find this kind of it's very difficult to choose because actually we are not the nuclear physicist. So we are trying to cooperate with some nuclear physicists, and even in our universities there is some professors to study the isomer many years. And maybe we can find some kind of isomer is suitable to the gamma ray lasers. I don't know exactly.
In fact, the major problem about the gamma ray laser was exactly the pumping problem, because people consider a short-lived isomer shorter than microsecond, for example, where inhomogeneous broadening is not really important. And in this case, you can probably find some way to pump, but the problem, you for short-lived isomer, you can, in principle, if you would pump enough, you could produce very good gain, but it's hard to pump because of fast decay, because pumping requirement scales like 1 over the 5th power of the wavelengths. So shorter the wavelengths, more power it is needed to produce population inversion. And people consider long-lived isomer living more than microsecond, even more than second. If it is more than second, then it seems to be possible to produce pumping, but then gain is so small that you are not able to exceed off-resonant losses. This is kind of problem, and either short-lived isomer or long-lived isomer, but for one or other reason, both don't work. And with your pumping abilities, one could reconsider this problem. So thank you very much.
Okay, well, thanks, Olga, for these comments and sharing this. Maybe somebody else has a question to Liming. Well, maybe I will ask a short question. So you mentioned conversion efficiency to X-rays on the order of 10 to the minus 4, which looks quite good. But what do you think is the main limiting factor for this conversion?
Yeah. Yes. Yes. Actually, this two, this one and this one, we really reaches to 10 to minus 4. 10 to minus 4. Frankly speaking, the baryton radiations usually the conversion efficiency is lower than 10 to minus 5. So actually, we increase it to 10 to minus 4 is really because we actually let the electrons through the DLA, and it's really quite effective. Produce the electrons with a quite high charge and very oscillation, the valent oscillations. So in this case, the conversion efficiency reaches to 10 to minus 4. Okay, so continuously increase the conversion efficiency is limited. Actually, right now it's limited by the laser, actually the laser power. If we use several petawatt lasers, I mean, we focus the laser intensity even more higher, and maybe we choose this near critical density target. So in this case, we can stimulate. There is a publication to show quite recently. They use a kind of mesh, small nano wire target, and shining target with 4 petawatt lasers, and they performed this experiment at GIST, and they really got quite high conversion efficiency, close to 10 to minus 3. Continuously increase to higher than 10 to minus 3, I believe we need to go to the QED, the quantum electromagnetic field. QED region, the conversion efficiency can reach to, for example, several %. So that's the right way, I think. Okay.
Okay, thank you very much. Well, let's move to the next talk, next speaker, and which will be presented by Jorge Roca, and he will be talking on picosecond laser filament guided electrical discharges in air at 1 kilohertz repetition rate. And Jorge, you will have your standard time allocated 25 minutes. Yeah, please.
Well, thank you very much. Can I share now?
Yeah, we can hear you. Yeah.
Okay, so I can share the screen.
Yeah, we see it. Yeah.
So you see the cover page of the presentation?
Yeah, it looks good. Yeah.
Okay, great. Okay, well, thank you very much. In particular, I would like to thank Olga, for the invitation of participating, right, and hearing, a very interesting preceding talk. So today I'll be talking on guiding electrical discharges in air at a kilohertz repetition rate with a laser filament. This is work done at Colorado State University, right? And I'm listing here my colleagues contributing to this work. And this work is enabled, right, by lasers, high energy, high repetition rate lasers we are developing in our lab. In particular, we have developed an ytterbium YAG laser that can produce joule-level pulses of picosecond duration at up to a kilohertz repetition rate, which is illustrated here. And so 1.1 joule at the kilohertz rates, kilowatt average power. And the schematic of the laser is shown here, has a kind of conventional front end producing 2 millijoule pulses from an ytterbium YAG regenerative amplifier that are injected into 2 cryogenically cooled ytterbium YAG amplifiers to produce 1.2 joule pulses before they are compressed into a high efficiency grading compressor and generating this 1.1 joule picosecond pulses I was mentioning. And as I mentioned, these amplifiers are cryogenically cooled. And this laser is, diode pump, right? Being ytterbium, it has the advantage of having a relatively long upper laser lifetime, millisecond, which is good to pump with laser diodes. And it can be pumped with, for example, 0.94 micrometer commercially available diodes, and lasing occurs at 1030 nanometers. So it has a very high quantum efficiency, that is the quantum defect, is only 9%, which makes it possible to extract the heat and operate high repetition rate. And we operate these amplifiers at cryogenic temperature because there are additional advantages. The thermal conductivity of YAG increasing several fold. In fact, for undoped YAG, up to 9 times. So you can extract heat more easily. And then pretty much everything improves, like the saturation intensity, which at room temperature is 9 joules per square centimeter, that drops to 1.7 joules per square centimeter, allowing for efficiency energy extraction. The thermo-optic constants also improve. And in addition, this system, which is basically quasi-3 laser level system at room temperature, becomes a true 4 laser level system at cryo temperature, right? Reducing the amount of laser diode power necessary to achieve, threshold for laser oscillation. So these amplifiers are what we call thick disk active mirrors, meaning there is a disk of ytterbium YAG, which are cooled from the back of the disk. The disk is just a few millimeters in thickness, so you have a large surface, cooling surface. The front face is coated with an anti-reflection coating. The back face of the disk is coated with total reflector. So light comes in, gets amplified, bounces back on the mirror, gets amplified again, right? So this is what's called an active mirror. Here's an illustration of one of the crystals. Actually, they are slabs, and the ytterbium YAG crystal is surrounded by chromium YAG to avoid parasitic lacing. And the amplifiers are quite compact. They're like basically 30 centimeters or so in length. You can see one there. With amplifiers, as with just 3.5 joules of diode pumping, we have achieved 1.26 joules actually of lacing from 1030 nanometers, with quite good stability and actually excellent beam quality, an M square around 1.3, and very good beam profile. And as you cryogenically cool, there is a limitation, that is the bandwidth of ytterbium strengths. However, after the entire amplification chain, sufficient bandwidth still remaining to compress pulses to around 4.5 picosecond. So this is the tool, right, that allow us to generate filaments with pulses of, for example, 200 millijoules at kilohertz repetition rate. And that's what's where part of the novelty is at, right, is to do filaments generated by high energy laser pulses at kilohertz repetition rate. So to do these experiments, we made a setup as indicated here, and all this is done in air. These are filaments created in atmospheric air. So the output of the laser I just mentioned, right, is basically directed to a lens that focuses the beam and allows to generate a filament, right, on the space of an optical table. And then we have different diagnostics for the filament. We certainly do fluorescence imaging, and indicated here on the picture, just with the lens and a CCD. And then we build interferometers, both one on axis, as indicated here on the figure, right, where we can probe the filament actually, and also transversely or at grazing incidence, and not done here. And then there is additional diagnostic, for example, transportable microscope to measure the energy deposited, and and so on. So from the interferometry, we study the formation of filaments at kilohertz and then lower repetition rates, for example, 100 hertz. So the top interferograms here, which are on-axis interferograms, shows basically time evolution, right, of the created filament, measured from the time of arrival of the laser pulse that creates the filament. So this is 0.3 microseconds, 2 microseconds, 3 microseconds. So you see the filament channel and then a shock wave, an expanding shock wave, right, that is created. And in particular, I want to call your attention to interferogram taking 10 microseconds prior to the arrival of a laser pulse, meaning that at 100 hertz, there is 10 milliseconds, right, after the previous pulse. And one can see that the air have practically completely recovered, right, by the time this pulse arrives. However, if the repetition rate now increases to a kilohertz, then the certain laser pulse that's going to create a filament sees the perturbation caused by the previous pulses, right? So this is 10 microseconds before the arriving of a pulse on the pulse train, but now they are separated by milliseconds. So the air does not completely recover and creates a permanent density depression. So you can see that shock wave and so on, they are the same, but you have the deflection of fringes that indicate there is a density depression. And analyzing the interferograms, we see that this density depression is around 20% of decrease, right, in the molecular density from atmospheric air. And you can see how this depression, right, builds up as you go from, let's say, 100 hertz to 250 hertz, 500 hertz, and 1 kilohertz. So it has been suggested in the literature, right, that this cumulative depression that occurs at high repetition rate can basically produce a channel in which you can basically guide, trigger and guide, electrical discharge. So we set up a modification of the experiment I just showed, in which we connected we introduced 2 electrodes with a hole in the middle, such that the filament is created basically on axis between these 2 electrodes. We connected a capacitor charged by high voltage power supply to one of the electrodes, grounded the other, so we can create, right, electrical discharges as the one shown here on the bottom picture. The top picture shows us the laser filament, right? There's no discharge here. You can see a nice fluorescent channel, right, from the creation of laser filament. On the bottom, what you see is a guided discharge, which is what I'm going to talk about on the rest of the talk. We use the same diagnostics. We use actual and basically gradient incidence interferometry, right, fluorescent imaging, right, and so on. And the first is just electrical data. What you see on the top frame here on the slide is just the output of a photodiode monitoring the arrival of the laser pulses at a kilohertz. So there is 1 millisecond separation between these 2 laser pulses. And each laser pulse that arrive causes breakdown, right? And causes a discharge. And then the capacitor gets charged before the arrival of the next pulse, and then a breakdown occurs again, and so on. So you are producing basically guided discharges at a kilohertz, right? So that's what's one of the novel aspects, and you can see quite stable, right, formation of these discharge channels as measured here by the voltage and by the current, basically carried by the discharge. On the right, you see the voltage, right? Like say the capacitor is fully charged, then the laser pulse arrives, and a few 100 nanoseconds later, right, there is breakdown, and there you have, the current pulse of the, discharge. So just for fun, I'm going to show here one of these discharges at a kilohertz. You have the 2 electrodes. We are applying voltage in between, and then we just shoot the laser, and you will see how that induces discharges at a kilohertz. Go. So there you have the discharges, right, going on basically at the kilohertz repetition rate. It's actually fun to watch when you're in the lab. So going back to what I was saying before, if you do this at 100 hertz repetition rate prior to the arrival of the laser pulse, pretty much the medium is already recovered. At the kilohertz, you are dealing with a density depression, which is caused by the accumulation, right, of the preceding laser pulses, which, as I said, causes, in our case, for the use of 200 millijoule pulses, a density depression around 20%. So now, one can try to predict from here, okay, how much reduction on breakdown voltage should this cause? And there one can use the very well-developed semi-empirical formulas that people have developed, for gas spark gaps, right? They are known for decades, maybe certainly, 70 years or something like that, maybe more, right? So this is very established expression. So if one uses those expressions in air, one can see that the measured 20% depression should cause about a 20% reduction on breakdown voltage. Here I'm plotting breakdown voltage versus pressure, right? So if you go from an atmosphere to, say, 0.8 atmosphere, 20% reduction, you expect a 20% reduction in voltage. However, the measurements that we took of reduction on breakdown voltage, which is plotted on here on the vertical axis, as a function of the energy of the laser pulse that induced the filament, is dramatically larger, right? For 200 millijoule pulses, we see a reduction on the voltage in this case, for a 2 centimeter gap, from around 42 kilovolts to less than 10 kilovolts. So you have a 4.2x reduction, not a 20%, right, reduction. And the same thing happens with longer columns. And in fact, with the channel, with the voltage available, we were able to break down discharges in 10 centimeter long gaps, right? Would normally would require more than 200 kV. And, we just did it with a power supply of less than 40 kV. But so what we are seeing here, right, is a very large reduction, right, on the discharge voltage. So then we did interferometry on the proximity or soon after the arrival of the laser pulse and measure what is the density depression. It was the value of density depression right after filaments created. And here's an example of a measurement, right? And this is the reconstructed density profile. And we see indeed that there is a density reduction more than a factor of 4. Okay, so what we are concluding here is that is not the cumulative action of many pulses creating this channel, which is the main contributor to the breakdown, but actually the density depression caused by each laser pulse that arrives. And this actually agrees well with particle in cell simulations coupled with hydrodynamic atomic physics code that which we simulated, right, that density depression. So what we did is we ran peak simulations for around 2 picoseconds and modeled the channel, right? What's the density, what's the electron temperature, a few eV, which then were used as an input to the atomic code RADEC by our colleague Slavas Liasev. And he ran simulations in which he basically computed, right, the density profile on the channel. And this is like, just a radial plot. So this is half the channel, let's say, this symmetric respect to this axis as a function of time. And this is the simulation, and this is the experiment. You see a fairly good agreement, right, on the fact that the simulations predict, right, a density depression of around 70-80%, which is in good agreement with what one would expect on measured reduction of breakdown voltage. And this is again results of the simulations of how the channel is formed, right, as a function of time, right? During the laser pulse, this channel starts forming, right, and then deepens, right, and stays actually for several microseconds at the maximum depression, right? And so our interpretation then is that it's not the cumulative effect, but rather that of a single pulse, which causes the breakdown. Then in that case, it shouldn't be much difference between breakdown voltage measured at 100 hertz and a kilohertz. And in fact, we did measure the breakdown voltage at these 2 repetition rate, and we see that they are practically the same. Okay, which agrees basically with that interpretation of the physics. What you see here is breakdown voltage as a function of the energy of the laser that generates the filament, and you can see that the results at 100 hertz and 1 kilohertz are basically within the error bars. Same thing for 4 centimeter discharge or a 2 centimeter discharge. So we continue this studying other aspects of the physics of this laser guided discharges. And as you know, many electrical discharges, right, start with the formation of a streamer, right? Like for example, right, atmospheric, right, lining. And so often, right, these streamers form close to one of the electrodes and propagate right across, right, with with a relatively high velocity. Well, we were fortunate to be able to borrow a very fast framing camera from Pierre Godin at the University of Rochester, and we were able to image right the basically formation of these channels with a 5 nanosecond resolution. Here you see a first framing image just taken immediately before the after the laser pulse arrived, but before the breakdown. And what you can see then is the formation of the discharge, and we see no streamer propagating from one electrode to the next. Basically, the channel forms all at once, fairly uniformly, right, through the electrodes, across the electrodes. So these discharges then appear to be streamless discharges. This is not new, right? Streamless discharges have been, observed, basically before, and these seem to be, streamless discharges. Other interesting thing that we observe is that as soon as the laser pulse arrives, immediately after, a small current starts circulating. But it takes several hundred nanoseconds, or in some cases microseconds, for the impedance to collapse and have basically the full discharge of the capacitor to occur. As you can see here, there is a pre-current that occurs as soon as the laser arrives, which is of the order of a few tens of milliamps. And then after a few hundred nanoseconds, there is a collapse on the impedance, and then we get a current pulse of almost 500 amps. Basically, the impedance of the discharge, right, collapses. This pre-current, we measure it to be pretty much directly proportional to the amount of laser pulse energy that forms the filament. And we further, study the effect of this, what we call pre-current, right, small current before through full, a breakdown by axial interferometry, right? And what we see is that when the laser pulse arrives, as I said, small current, tens of milliamps, starts flowing. And if we take axial interferograms, we see the channel, but we don't see a connection between the channel and the electrodes. We were looking here is down a hole in one of the electrodes, right? And we see that the filament created channel doesn't appear to be linked, right, with with electrodes. So we interpret that there is a high impedance glow discharge that immediately forms that carries this relatively small current from the filament to the electrode, and then after a while, full discharge arcs form. This high impedance glow discharge collapses into arcs that start linking the channel, central channel, to the electrodes. And at that point, the impedance collapses, right? And you get this very large increase in current. And then, of course, the channels, right, get more pronounced, right? And that's how the current, right, is conducted. And often, right, what happens on these gaps, which is this very small gap, right? It's like 1.5 millimeters, or just slightly less than 2 millimeters radially, this distance. Mostly this is neglected often in the formation of, basically these discharge-guided filaments. But we found out as the channel is the order of 10 centimeters or so that we made our experiments with, this cannot be neglected, right? This plays a role. And in fact, that can be seen, right, if one creates discharges with constant E over N, where E is the electric field, N is the molecular density, right? As many of you know, the E over N, right, is a scaling parameters of discharges, right? So we made discharges at equal E over N. We made discharges through a 2 centimeter gap and through a 4 centimeter gap. And what do we see? if we measure the delay between the arrival of the laser pulse and the breakdown, we see that actually the discharges through a 4-centimeter channel break sooner, right? Have less delay than the one through a 2-centimeter channel, right? And the interpretation of that is, since we double the voltage to maintain the same E over M in the 4-centimeter discharge respect to the 2-centimeter discharge, if the voltage drop along the channel is the same, right? They're created by the same filament, and so on, right? By applying twice the voltage, we are over voltaging the gaps, right? And then there is this over voltage of the gap that reduces the time delay between the arrival of the laser pulse and the breakdown. Again, basically pointing out that you cannot neglect, those little gaps, right? If you have a discharge of the order of centimeters, so let's say tens of centimeters. So in summary, we have generated guided stable discharges at of the order of 500 amps at kilohertz repetition rate in air, as shown there. So the picture on the top right. We measure a reduction of 4x on the voltage necessary to cause the breakdown. And these discharges are observed to be free of streamers, right? We see that as soon as the laser pulse arrive, there is a current of tens of milliamps that we call it pre-current that starts circulating, but breakdown does not occur until hundreds of nanoseconds or microseconds later, where arcs form between the filament and the electrodes. And so concluding that the air gap between the filament and the electrodes plays a significant role in the breakdown. And as I mentioned, our interpretation, right, of the data is that is the density depression caused by a single laser pulse and what really causes the breakdown, with cumulative effects only playing a secondary role. So we want to thank our sponsors. This was done with support of Office of Naval Research and a DOE Vannevar Bush Faculty Fellowship. Thank you.
Thank you very much, Jorge, for interesting talk. And now, who has some questions, please? Well, I have this question maybe while others also think of their questions. In this filament, since this is kind of processes of self-focusing and probably ionization, so the filament itself, it's not quite uniform. So the question whether you see any effects of this non-uniformity of the filament.
Well, I mean, of course, you're right about ionization mechanism. These are picosecond pulses, right? So optical field ionization plays a role, but then basically is collision ionization, avalanche ionization, right? What really takes over, because these are pulses of like 7 picosecond, right, duration. The energy of the pulses basically is sufficient to create very long channels, okay, much longer, that we are doing here. So they can make actually quite, uniform, because we are using a lens to be able to do this on an optical table before, right, the self-focusing that you mentioned. Letting this beam collapse by self-focus, you take something around 50 meters, right? So to have it on an optical table, then we put a lens, right, to help the filament form, right, in a small optical table. But the length of the filament still exceeds, right, the distance between the electrodes, particularly, right, on the case of 2 4-centimeter discharges, right? Like I was showing, I think, in one of the slides right at the beginning, the one that has the picture, right, of this one, right? You can see here for 10-centimeter discharge, right, the filament continues, and of course here start being not uniform. But once you move this to 4 centimeters or 2 centimeters, the channel is quite actually uniform, quite uniform.
Thank you. And I see Olga has a question, please.
Yes, I have a couple of questions. One more or less obvious, but nevertheless, you mentioned that I'm a little bit confused, because at the beginning you were showing that increase in the repetition rate to kilohertz should help, right? but then you concluded with the other experiments that it does not, or it's already an effect of single pulse ionization, right?
Yes. So what we see is, what we see, right, is that we measure, right, by interferometry, when we just do it at 100 hertz, right, we measure a density depression of around 20%, which should reduce the voltage approximately by that amount, right? However, we measure, an 80% reduction in voltage, right? Like 4 times larger, right? So this cumulative, effect certainly contributes, certainly help, right? But it's not really the driving force, right?
I see.
When you basically create, filament, right, by a single shot, right, the depression gets to be, around 80%, right? While if you basically look at what's the depression right before this arrival, the arrival of this pulse, right, then the depression, right, is like indicated here, right, at kilohertz, only 20%. So the cumulative effect certainly still contribute, right, but it's not the dominant cause. That's our conclusion.
Thank you. And a second question about what is kinetics of this plasma, what is the chemistry which is involved, if it's possible to maybe complement your experiments with some spectroscopic study to see what's going on with concrete ions and how it develops and what's going on in chemical reactions. What do you think?
Yeah, well, that's very good, thought, and we have done that. We didn't display the data, right? We have an spectrometer and we have taken, right, spectra, right, of of the plasma, right, because this is in air, right, it's complicated to model, right? Slava started working on it, right, but didn't complete a full model with all the chemistry and all the collisions and reaction, right? It's a complex media. We see mostly emission from molecular species, basically either molecular ions or neutral molecules, basically.
Thank you.
The temperature is estimated to be just a few eV.
Okay, thank you. Other questions? Let me see. I don't see more questions, so thank you very much, Jorge. And now, Karuna Isyan, as we know, could not unfortunately take part in this session. So then we go straight to Art Verhoef. I see he is also here. And he will talk about multiphoton super resolution microscopy. Please, Art, go ahead. Yeah.
Thank you, Alex, for the kind introduction, and thank you to Olga for inviting us. Before I share my screen, I just want to say Alma just jumped out of the meeting because we're sitting here next to each other, and it looked like the bandwidth was maybe not good enough to be on the same Zoom with 2 computers, so she will join back right after I finish.
Okay, great, yeah.
Right, so I will present something about our work on multiphoton super resolution microscopy. Let me see, I want to make the, right. So there's a couple of other people except for the co-authors that I want to also especially thank the last persons here, Dylan McCready, and who helped us to get some nice samples to measure with deep tissue super resolution, and Michel Antolovich, who helped us to get this the special detector for this work. So as I'm talking about super resolution microscopy, the first thing to talk about, of course, is resolution in microscopy. And the thing that matters there is what is the smallest separation of objects that you can really tell apart. From classical optics, we know since 150 years already that there is this diffraction limit, the Abbe limit, that is given by more or less half of the optical wavelength divided by the numeric aperture of the focusing element that you're using. And when we talk about super resolution microscopy, that is any microscopy method that manages to go beyond this limit. A couple of years ago, 10 years ago almost, a Nobel Prize was given for this kind of work, and it's still a very active field of research. So when we want to go beyond the diffraction limit, one of the first methods that was demonstrated is using a very few emitters that are switched on and off while you're measuring, and these few emitters are far enough apart to be isolated emitters, and you can start to fit where their exact position is, rather than that you get a diffraction limited spot of it. You can get their exact position by fitting them kind of the peak of this diffraction limited spot, and with that you can get a higher resolution. That gives you a scalable improvement. The longer you measure, the longer you kind of get signal from a single emitter, the more precise you can determine its position. It works very good with thin samples, but it needs very specific conditions. You need to be able to switch emitters on and off. You need to have them switching on and off at a specific way, such that you have few enough on at every given time. So you need specific conditions for that. Another way to do it is to engineer your point spread function, for example, as done with stimulated emission depletion, where a donut beam depletes the outer part of the excitation volume. Again, that can give you a scalable improvement. The more power you put into that donut beam, the more you restrict the staying behind excitation to a very small region. Again, this works good with relatively thin samples, because this donut away from the focus doesn't restrict the light as much anymore, or the excitation as much anymore. And you need an additional laser to make that donut beam. Another way to work with this, or to get beyond the diffraction limit, is to use what you could call spatial frequency mixing, or down conversion of spatial frequencies. In more simple terms, that's are methods that are called structured illumination microscopy or image scanning microscopy. That those kind of methods give you a moderate improvement, maybe a factor of 2, but you do not need any additional lasers, and it will work really with all samples that you can make. And the last method that you could use is a little bit similar to the second method that I talked already about, but in this case, it's using just normal fluctuations that are naturally occurring with almost every fluorophore. Then you get phenomenon like anti-bunching. Any given fluorophore, any given emitter can just emit a single photon at any given time and not emit 2 at the same time. So another way is statistical optical fluctuation imaging, called SOFI, or radial fluctuations. Those are built in a lot of new microscopes at this moment. And also that gives you kind of a moderate factor 2, maybe. Sometimes it can be a little bit more if you do higher order correlations, but a moderate improvement. And it again works with most samples, with most fluorophores that you can imagine. So the other part of my title was to do it with multiphoton microscopy. So when we do multiphoton microscopy, what would be the resolution then? Again, the diffraction limit, you can have it as a Rayleigh criterion with 0.6 times lambda divided the numeric aperture, or with a full width half maximum at 0.5 times lambda divided by the numeric aperture. And what is important to notice as well is that when you focus your light and you do multiphoton microscopy, the effective spot size actually becomes smaller with higher nonlinear effects. So for 2-photon microscopy, the effective spot size becomes a factor of square root of 2 smaller. With 3-photon microscopy, it becomes a factor of square root of 3 smaller, because the point spread function is taken to the second or to the third power. However, if you compare it to what you would do for the same fluorophore with single photon excitation, you multiply the wavelength by a factor of 2 for 2-photon or by a factor of 3 for 3-photon. So in the end, for multiphoton microscopy compared to single photon effects or single photon methods, you lose a factor of square root of 2 or square root of 3 in resolution. So we actually would, in our multiphoton super resolution microscopy, the first goal is to actually even just make up for that factor, square root of 2 or square root of 3 loss. And you will see in the next slides that we actually managed to do that. So advantages that are of multiphoton imaging is that due to the multiphoton, the nonlinear effects, you suppress out of focus signals. And when you would do single photon excitation, you would need actually a pinhole to reject the light that comes back from out of the focus, from not inside the focus. And with 2-photon, you get this natural restriction of the fluorescence to come from only around the focus. And with 3-photon microscopy, this optical sectioning is even stronger. So the 3-photon microscopy would give you the best resolution and the best optical sectioning. Here is just one other advantage when you go to multiphoton microscopy, multiphoton excitation, is that you suppress, even when you add losses, you suppress the out of focus signal. If you get too much losses in your sample, when you go deeper and deeper, at some point you get to a point where the 2-photon signal from the top could be comparable to the signal that you get from the focus. But then in that case, 3-photon microscopy still gives you this very good sectioning. I think I will just skip this slide here. So when we want to improve resolution with multiphoton, as I was already explaining in the beginning, there is these 2 methods that give you a limited, kind of a moderate improvement of the resolution. And we are going to use those 2 methods and combine them to get to a resolution that is better than what you would get with diffraction limited single photon imaging. So the first part is to do image scanning multiphoton microscopy. In this case, we use an array detector that helps to resolve the point spread function. This array detector, we put it at a so-called confocal point. So when you backpropagate your beam through your scanners, then you can focus it back to the array detector, where you can then resolve basically the point spread function. And so in this case, that looks like what you can see here. Maybe I can get a pointer. So multiphoton microscopy, you have a femtosecond laser, in our case, a femtosecond fiber laser, that we use galvo mirrors to scan the laser beam over our sample. When you do normal multiphoton microscopy, typically you have your detector as for example, a photomultiplier as close as possible to your sample, where you do not do this confocal detection. In our case, with the array detector, we need to do this confocal detection. So we need to go, our signals need to travel all the way back, and then with a dichroic beam splitter, split and sent to the detector. So mathematically, you could say that each pixel from this array looks at the excitation, at the excited volume from a slightly different angle. And that's basically what you're seeing here. The detection point spread function is shifted a little bit to the side, which makes it, which gives you in the end then an image that gets a higher resolution when you combine all the different detectors. So here you can see the normal point spread function when you would do just three photon imaging in the center panel on the top. That would be the detection point spread function of each individual pixel of our array detector. And when you do the combination of all these pixels, you get to an even better confined point spread function. So we get to an improvement of about almost a factor of 2, I believe. So we did then measurements on a sample made of where we dispersed nanoparticles, quantum dots on a blue emitting quantum dots on a microscope slide. When we measure with normal standard 3-photon microscopy, we get a full width half maximum of those sub-diffraction limited sized particles of about 290 nanometers, which corresponds nicely to what we would expect for a measurement of a diffraction limited spot focused with about a 1.2 numeric aperture objective. When we do the image scanning microscopy with this sample, the resolution already improves to a little bit below 190 nanometers. So about a 50% reduction of the point spread function. And then we can apply an additional deconvolution to our images, to the images that we obtain. And with that, we can get to a resolution of about 126 nanometer, which means that we get a resolution that is about 8 times smaller than the wavelength of light that we're using. When we do these measures, when we would measure the same sample with the same objective in a standard confocal microscope, we were obtaining a full width half maximum of a resolution of 220 nanometers. So with the image scanning microscopy, we already are better than what we would be with confocal microscopy. The advantage of doing this with 3-photon microscopy is that we can image deeper into samples. So what you see over here on the left-hand side are 2 times 3 images. One's just measured with the 3-photon imaging, where you can see that there is a kind of the image looks comparably blurred compared to the other images. And that's because of course, the resolution is not as good. When we do it with the image scanning microscopy, we get much sharper images. And when we add the deconvolution, we get really sharp images where we can see a lot of detail in there. And on the lower the lower set of images is taken at a depth of about 100 micrometers, which is basically impossible with confocal microscopy. If you want to measure from the top to the bottom the same sample, you would have bleached the lower part of the sample before you even reach it to measure it. So you basically get no signal at all. So with 3-photon microscopy, you're able to get that deep and still get a little bit over 100 nanometer resolution. So the next part is to combine this with the other methods to get a moderate improvement of resolution using optical fluctuation imaging. When you have a sample, especially when it's a sample with quantum dots, you'll see that those quantum dots switch on and off kind of randomly with time. And that switching on and off, we can then use to improve the resolution. So when you evaluate the blinking statistics of these quantum dots, you can use that to get a higher resolution. Here, you can see on the left a standard 2-photon image of and a line out through that image of the same quantum dots, where you can see that it's a washed out blob where you would not be able to tell whether there is 1, 2, or 3 quantum dots in there. And on the right hand side, you can see the same sample when we did SOFI post-processing on those images. And you can see that there's actually several isolated emitters there. And then finally, we used the same method to combine this image scanning microscopy on a quantum dot sample and SOFI on the, so image scanning microscopy and SOFI post-processing on one measurement, where you can see that we get over here about 2 quantum dots that are quite nearby. You can still see from the image that there are 2 quantum dots. And over here on the middle panel, you can already see that they're well separated. And in the rightmost panel, the separation is even better. When you plot it as a line out, you can really appreciate the resolution improvement that you get when you use these 2 super resolution methods. And in this case, we managed to get to a resolution of really about 100 nanometer. So we get to pretty good resolution improvement. And with that, I'm at the end of my presentation. So I want to thank you for your attention.
Thank you very much, Art, for interesting and informative talk. And now it's open for questions, if any questions there. Well, I have this question, Art. So when you go to like higher order multi-photon processes, you kind of have 2 different things happening. One, you change wavelengths, of course, but on the other hand, your signal to noise also will change, yeah, because the signal that you obtain also is changing, yeah. So how this actually, how this interplay happens, and is there any kind of optimum? And of course, there can be also some other limits when you go to a high and high order of multi-photon processes. Yeah.
Thank you, Sasha. That's a very, very good question and a very valid point. That's kind of an issue that you get already when you go from a single photon imaging to multi-photon imaging to 2-photon imaging. One issue that you would have with when you want to do in vivo imaging is that when you excite with blue light or with ultraviolet light, that you kind of cause some chronic damage. So you would not notice today that you're damaging for example, embryos that you're imaging, but the next day they're suddenly all in a very worse state. And when you would do it with 2-photon microscopy, what you need to be careful of is that you do not damage it right away. But if you do not damage it today, and you do not damage the cells while you're imaging, the next day they're still as healthy as they were the day before. So that is one thing. Yes, you need to take care that you're below a damage threshold of blowing things up right away. But when you stay away from that, you're actually better than with single photon imaging, because the ultraviolet light that you're using for the single photon imaging is illuminating the entire sample and doing damage everywhere. And also, the signal to noise is then one of the things that you need to take care of. Sometimes you need to, it takes more time to do some of those measurements. When you compare confocal imaging to 2-photon imaging, and even 3-photon imaging, when you have bright enough fluorophores, you can reach about the same speed, because often the speed is limited by the optical components, the scanning mirrors, for example, that you have in there. So, yeah.
Okay, well, thank you. And I see another question, Ranjit Singh, please, your question.
Thank you for your talk. Could you please explain the concept? How do you extract useful information from noise for improving resolution?
Let me try to understand the question right. Right, when we obtain images, let me see if I can even get back in. Right. For example, from images like these are this is a spinal cord that was labeled where the cell nuclei were labeled with a blue fluorophore. So anything that shines back blue light is, or anywhere where the blue light comes back from, that is from cell nuclei, right? And the kind of the structure or that you see in those images is telling you then something about the nuclei. In the standard 3-photon microscopy, what you see is what you get, and right, the resolution might not be good enough to see all the details that are really there, but that is what you have to live with when you do the image scanning microscopy and the retrieval of that. Again, this will not invent any new details for you. When you start to do deconvolution, that is where you have to be mindful of what of the results that you're getting. So you would want to compare them to either something that you already know about the sample, or at least you want to be mindful of not letting this run for too much time, that it's getting you kind of its own interpretation. Does that answer your question?
Yes, thank you.
Okay, thanks again, Art. And yeah, let's now next speaker is Alma Fernandez. And Art, you probably have to switch, yeah, now?
Yes, I will mute and Alma can.
Okay. And Alma will talk about nitride uptake in roots with Raman microscopy.
Can you see my screen or?
Not yet.
Now?
Okay,
Yes.
now we can see it. Yeah, please go ahead.
Okay. Wait a minute. Hello. Thanks very much to Olga and to Olga for the invitation and to Sasha here for leading this session. Today I am going to talk about our work on trying to map nitrate in roots using Raman microscopy. Before going ahead and not to let important people here at the end, I want to recognize the our collaboration with Dr. Sakiko Okumoto from she's from the Department of Soil and Crop Sciences, and she's a molecular biologist, very motivated to try to understand how plants manage nitrate at the cellular level. And also a very, very special thank to Dr. Marlan Scully, who allowed me to buy a big amount of things that I use for this research after some other things didn't work as right away. Well, yeah, you see Marlan with his nice hat and Dr. Okumoto, you can see the picture here. I was one slide before. So the motivation of our work is really to try to map nitrate in roots at the cellular level, and not just in root, but that's where we started. Because it's very important. Roots are very important because there is something called the rhizosphere that is basically the interface between soil and the plant itself, the root, where many important things happen and where the plants make use of microbes to utilize a lot of nutrients and other essential things that they use for important signaling. And one of these things is nitrogen, that is the most essential micronutrient for plant growth and is mostly available in plants in the form of nitrates, although there are some other sources of nitrate too. But in this case, and for this work, we basically utilize nitrate, as you will be seeing quickly after these first slides. And as I mentioned, some micronutrients and some substances around the plant rhizosphere are used, or up there in the air, are used for the plants to survive, and as in many cases as a signaling to manage or control some important physiological processes for survival. One of the things is root system architecture and floral induction and seed dormancy, but I'm not so an expert in any of those things, but we were asked originally by Dr. Okumoto if it was possible for us to measure nitrate concentrations below 10 millimolars. So and we thought, like, well, we can give it a try. And IQSC, this as you can see, this is a collaboration between Department of Soil and Crop Sciences, but also the Institute for Quantum Science and Engineering, led by Dr. Scully. And we started looking into this problem slowly, and why the root architectures, why nitrate and the importance on root architecture? Well, because that's the way the plants will determine how roots will be spread in the soils, how they are going to be able to get better, more nutrients, and depending on if the concentration of nitrate or it's going to be high or low in the soils, that will signal the plant how to develop the roots, and in order to survive in the environment. All the way this happens is not quite well understood. Actually, far away from understood, being well understood, and we are basically starting here. And what we offer to this work was the capability or possibility that we could determine nitrate at the cellular level or in roots, and in a non-destructive way. And it's important things to measure here is to see that there are different ways how these plants evolve depending on different growth conditions. And I just put this as an example for you to have an idea of how different things can go. But also another important thing to mention is that in this is Arabidopsis roots. Specifically, I'm showing these ones as an example because this is what we have been dealing with. Because one advantage of Arabidopsis is that there are many types of mutants, and there is like this is like the fruit fly from for plant pathologies and biologists, and this is very helpful when you want to understand some phenomena. Again, I'm a physicist, so many things here are totally new, or were totally new for me. But important to show that the cell diameter is like between 10 and 15 micrometers, especially in this zone that they call meristematic zone. And after that, the cells start being bigger. But this means that you need a way to not just take the whole root and just measure, for example, nitrate with some destructive methods, but these micromolecular biologists are trying to understand different aspects of how nitrate is accumulated. And in this research, we find things totally unknown for them. They were very surprised that this, with the data we were obtaining, and it was a long road to get to that point after figuring out different hurdles we have through this work. And again, our main motivation is to develop a technique and apply this technique to nitrate mapping at the cellular level to better understand how plants manage nitrate and how this could help to develop real crop varieties in the future that can have a better way of using resources and all that. And there are some other ramifications of this work that, well, I could talk about that if I have more time at the end. So some of the existing methods that it is not my area of expertise, but this is what typically is done for detecting or measuring actually nitrate concentrations in these roots. And one method that is used a lot is the salicylic acid method, and where they do absorbance measurements of nitrosalicylic acid. So this involves some chemical steps and to then do some measurements of absorbance, and from there be able to, with the appropriate calibration curve, be able to determine nitrate concentration. Other one that is maybe more known among different disciplines is the high pressure liquid chromatography. And this is also a method that requires, it's not so cheap, although these machines are not that expensive, according to me. It seems like $20,000. But still, you have to have an involved process for the sample preparation, you need you put them in nitrate and liquid nitrogen, for example. Same thing with the other method, because you want to extract all way it in there out of these cell membranes, and this is all a process. And one of the things that all these methods require is enough sample, and then you in order to measure, you need to get many seedlings. And I mean, you are not going to go like with some micrometer pieces of your seedling or your root. There you have to collect many. The less amount of root you get, the more seedlings you will need to produce. This is of course destructive and involve laborious sample preparation. So again, our motivation is to test this tool and actually develop the protocol for measuring and try to quantify nitrate in the roots. And we try to do this as a mapping procedure and not just at a special point on the roots. And in this way of being able to check at different positions at the root with very precise control stages, we found different new things that seems are not available at this moment for other for the biologists to use it as another source of information to understand how plants manage nitrate. So when we started using an available HORIBA Raman microscope at IQSC, and then we used different solutions of potassium nitrate and start trying to see how what is the minimum concentration we can detect with that system. And we were limited to 100 millimolar, 10 millimolar. We couldn't see for scanning like 30 minutes. This was not possible, and the point is we needed a method that it would not require to scan forever, because the plant shape morphology, and if you leave this for all the night, your water also evaporates. So there are many tricky things to take into account here. Of course, you have the fluorescence of the containers you are using, and so on and so on. And we tried also using Fourier transform cars of nitrate in water for the same thing and compare. But again, I think our system has a lot of potential to be improved, but with the limitations we had at that moment in terms of the stages we were using to do the scanning for the Fourier transform cars, we were also at the same limit that we were seeing with the HORIBA lab microscope. So we were fortunate to get support for this work. And again, one of the challenges that we had for developing or putting together a new system was to generate in signals with enough signal-to-noise ratio so that we can be able to detect nitrates. And the goal was to do it in the root, of course, and that concentrations below 10 millimolars, because it seems that in the soil it is like 1 to 5 millimolars, or though many studies they go way up to 175 millimolars. Our collaborators in soil and crop science, they say like it makes no sense. We really need to try to do this study at relevant physiologically relevant conditions, and we have to go really down as much as possible. We are now with the detection limit like 1 millimolar, as I would show later, but we still need to go better, I think. And one of the problems is, of course, you are dealing with biological samples, so you have to do all this without burning the samples. So you have to play out with all the parameters, make sure the things you are using are not creating to contain the medium where these samples are put, that this is not interfering with your Raman signals. And of course, you have to deal with fluorescent background where you have to do, well, do I do more scans and then less power applied to the sample? So it's all a trade-off that it seems very straightforward at the beginning, but you have to have the patience for that, and good collaborators that can deliver a lot of plants, seedlings, because it's also not that straightforward to make them. Is it good? Is it mostly standard protocol, but for us it took us a while to determine the growth conditions, make sure that these things are reproducible, have our controls to make sure that the growth conditions were not affected during growth, and also that not human extra help with putting the samples in the wrong direction, because these plants, the roots to grow, they need they typically to grow with gravity, and if people come and go to the growth chambers and then they leave the samples in a horizontal position or semi-horizontal position, then you have a problem. So this all have to be taken care of. And here is the
Alma, excuse me, can you come to results, because we kind of running already quite close to the next session.
Okay, no, I'm very close. It's like
okay, please, yeah. Mm-hmm.
Okay, very nice. So we just developed got very cheap and simple Raman spectrometer that we put together with a microscope system. And here is our 5-day-old seedlings. And this is the Raman spectra we are getting. And you see for different concentrations, you see that the nitrate peak that is around 10.4 is centimeter -1. You can see it here after background subtraction and some post-processing of these signals. The first thing we did was to calibrate the nitrate content and to be able to measure in the plants. And then we measure at different positions in the root based on the different zones that the roots have, and these zones are typically very well defined, starting from the tip of the plant until what is called the maturation zone, that is above 4 millimeters, 6 millimeters, 8 millimeters. And then what we could see here, these results we got with the Raman were validated with the salicylic acid method, the special variation that our collaborators from Dr. Sakiko were applying. And the good news, they couldn't measure like with that precision we have, but they cut pieces of 0 to 3 millimeters and 3 to 6 millimeters. And these results are confirming our Raman measurements. One thing that it was important to check, it's that as you can see here, you have that there is less nitrate on the tip side than when you are approaching the leaf side, that is the size after 4 millimeter of measure from the tip of the sample. And one thing that we are seeing is saturation of nitrate, and this is measured on the maturation zone. And then we have measured this for different for seedlings that have grown in different nitrate different agar media with different nitrate concentrations. And you can see that there is, after 10 millimolars, there is a saturation of nitrate, and you see this peak at 100 millimolar. We don't include it here because at 100 millimolar, the phenotyping of the roots was totally different. So it makes no sense to do the comparisons for the other plants below 50 millimolar. The phenotyping was similar, so we kept on this region to determine this saturation zone. And well, in conclusion, we have present here the possibility of using Raman microscopy, where we are shown here how Raman microscopy can be very useful to understand nitrate management in plants, and how mapping of nitrate could be done with Raman microscopy. Actually, we want to go to use CARS microscopy, FT CARS, because we think now we are improving our system for doing that in order to improve the spatial resolution, because even in this the transversal, we were going through the longitudinal part of the plants, but the transversal concentration of nitrate, we still want to work with that. And this is a company, Mesaphotonics, that has shown a great interest to work with and do this work, and also go for trying to apply quantum cars and on SRS to this work. Thanks very much.
Thank you, Alma, for your nice talk. Well, I see already chairman for the next session period, but maybe one short question, if there is any. Well, so far I don't see any questions, raised hands. Thanks again to everybody who participated in this session. We learned about many applications of laser techniques. And well, there will be a short, maybe 5-minute break before the next session. So thank you.
Thank you, Sasha. Hope to see everybody in 5 minutes. We have only 5 minutes left.
Okay, bye. Thanks so much.
Bye.
Bye.
Bye.